Hey, this is Horner. We're going to look at the second section in this unit called the ray model of light. So the ray model of light, which ignores diffraction, so that's spurting out of the waves, is valid as long as any apertures, so that's the size of the hole that the light goes through, are larger than about 1 millimeter. So if you make a pinhole camera, you would have to make sure that that pinhole is at least 1 millimeter wide. Otherwise, this would be a little bit more difficult to do. A light ray is basically a line in the direction along which energy of light is flowing, and a laser beam is a really good approximation for light rays. So here we would have light rays that would be generated by the laser, and then this would be the laser beam itself, and all the light rays are traveling in the same direction. The next slide here just basically shows that light does travel in a straight line. Light rays can also cross, so they don't interact with each other. If you have two laser beams, you shine one and you shine another one, when they hit each other, they won't be affected in any way. A light ray will travel until it interacts with the material, so it either will reflect off that material or it will bend, and we call that refraction. Sometimes it will scatter, and that just happens within a material, and other times it might hit a material and then be absorbed. So there's a lot of different interactions that we'll see, and we'll talk about those a little bit later. An object is the source of many different light waves. And so each one of the points on this Christmas tree would give off light rays. And then objects can be self-luminous, they can create light rays, or they can be reflective, that only rays that originate somewhere else. So if you're in the dark, you won't see this Christmas tree, but if you have light shining on it, it will reflect light in all directions. The next one here just shows how the eye sees. So the eye sees by focusing a bundle of rays, and when it does that, the image is flipped upside down as it goes through the lens of the eye. So our eyes then have to, when they have this focus on it, goes to the brain, and the brain flips it back over. Self-luminous or sources of light create light rays themselves, so that's like a light bulb or the sun. Everything else is reflective, so if you have a picture or you have a mirror, you'll see light coming off that. These objects include like a piece of paper or a tree. Then those are reflective objects. A good ray source would be a laser beam. So there is not really any true ray source, but a thin beam from a laser is a pretty good approximation of a single ray. A point source would be kind of like a Christmas light, so we've done a lab with those, and so you'll see light rays come out in all the directions. And then an extended source would be a light bulb, and we also did that. So here the entire surface is luminous, so every point on that surface is like a point source. A parallel ray source is similar to a flashlight, movie projector, anything that produces a parallel ray. Rays from a very distant object, such as a star, are almost parallel, so they're pretty close to that. A ray diagram is just something that we're going to use, and you're going to use these a lot, and they help us just use a few rays to simplify the situation. So in reality, light rays do originate from a single point, and there's a lot of them, but we're only going to use a few. We do some ray tracing. So here's the first example. This is Quick Check 18.1. It says the dark screen has a small hole, so here's our small hole. It's about 2 millimeters in diameter. The light bulb is the only source of light. What do we see on the viewing screen? So we've actually done this before with our pinhole camera, and if you remember, you get an upside down image because the bottom, when it goes through, is projected on the top, and the top light ray comes through, does not bend, and so it becomes on the bottom. Here's another one. So here I've got two dots, and they shine through this slit. They want to know, what do we see? And actually what you'll see are two long lines that would be projected on the viewing screen. You would not just see the two dots, that you would get light rays that would go through, and they would project in the back here and have these long lines. In order for your eye to see an object, rays from that object must enter your eye. So you really can't see a laser beam traveling across the room because there's no light that enters the eye, and you don't ever want to shine those into your eye. So this is the case for a ray or a parallel ray light source. If you take a laser beam though and you go outside in a foggy morning and you shine it, it's really cool because you can see that because it scatters off of the water droplets. A point source and an extended source emit rays in every direction, and some of those rays enter the eye no matter where it's located. So a point source, kind of like our Christmas tree light, or an extended source is visible to all observers. So here I've got two people, they both see the point source, and then this person does see extended source, and then this person over here would see it if they were facing the right direction. Diffuse reflection is a process of reflecting light in all directions. And scattering is a process in which single rays are broken into many weaker rays that leave in all directions. So here we've got an incident ray. It breaks into many weaker rays that scatter in all directions. So that's what we call scattering. And that's kind of what we do when we get a diffuse reflection. So when you read a book, every point on the surface of the page is struck by the ray from a lamp. And then because of this diffuse reflection, those rays scatter in every direction, and some of those enter your eye, and you can actually read what's on the page. Lasers are visible when you have little particles, kind of like we were talking about the fog or water droplets or smoke or chalk dust or anything like that, and they scatter that light in every direction, so then you can see it. Some of those rays do come out and hit your eye. Other ones go in other directions, and you don't see those as they go out in those other directions. A shadow, if I have an opaque object, that's just an object that light cannot go through, it will leave a dark shadow behind it. So when we have a point source, the shadow is completely dark around, and the edges of the shadow are very, very sharp when you do that. If I have an extended source, then I get a lot more rays, and now I get something called a penumbra and an umbra. These are two different parts of a shadow. So the penumbra is the kind of the hazy outside, and then the umbra is the really dark inside. The shadows overlap, so the shadow is no longer sharp. So remember, with an extended source, you get a fuzzy shadow, and then with a point source, we got a very sharp shadow. So that's the difference between the two. Depending on the size of the source, there's often a true shadow that no light reaches, surrounded by a fuzzy region of increasing darkness, of increasing brightness. So you can see the same type of thing when we look at this bulb as we look from 3 points on a screen.